All right, everyone, let's look at question 8 from section 1.4. So on the right, these horizontal line segments, we're given a graph of the derivative of function. So what we want to do for part A is come up with a graph of what the original function, the parent function g, looks like based on these derivatives, or based on this derivative graph. So another thing I want to focus on, we are told that g needs to be continuous. So we'll give a more, mathematically rigorous definition of what a continuous function is. But for right now, we'll go with the definition that, more informal definition. There are no jumps or holes in the graph, or I can draw it without lifting my pencil off the paper, but we'll go with that. So what can we say about the derivative here? So basically the derivative of g takes either one of two values, either +1 or -1. So what does that mean? So let's just talk about those two cases. If the derivative is +1, then what does that mean about the function g? Well, one of the ways we've talked about derivatives and how they're related to the original function, especially in terms of graphs, is that the derivative of a graph tells you the slope of a tangent line. So we can use that same kind of interpretation here. So we know that from -3 to -2, the derivative of our function is 1. So what does that mean about the slope of g? That means the slope needs to be 1. So let's kind of divide off that part of our graph. I know that to the left of this line, we need to have a constant slope of 1. We're not really told where this graph begins, but let's just pick a place. Let's start at the point -2, 0. And again, this is very arbitrary, but I want to have a slope of +1 from here. So I need to have a straight line like this. So that has a slope of 1 everywhere. So when we get to that dividing line, then what do we need to do? Now we need to have a slope of -1. So what's our graph going to look like between x equals -2 and x equals 0? We're going to have a slope of -1. And that slope's going to be constant. So we need to have a straight line like that. Okay, and now we're going back to a derivative of 1. So I'll make a dividing line here. But basically, we're going to have the same behavior as last time. We're going to have a straight line segment with a slope of 1, terminates here, and it should make sense, or hopefully it makes sense, that we get back to the same, level of y equals 1. And that's because we have the same rate of change as the first line segment. Or sorry, as the previous line segment. So whatever we decreased in the second segment, we should be able to, that increase should, so to speak, cancel out in the next phase here. And then finally, our derivative goes back to -1 again. So we're going to have this constant downward slope of -1. So again, I think I mentioned this once, but we are not told a point where this graph goes through. So basically, your graph might have the same shape as mine, but it might be higher or lower. So that part's negotiable. What is not negotiable is that we have these slopes. So for these 4 different segments here, we need to have these. Basically, they have to be straight line segments because we have constant derivatives, and because we have constant derivatives, we know exactly what those slopes are going to be. So that should be all for part A. So part B, on what intervals other than 0 to 2 do you expect y to be a linear function? Okay, so I think part B, we can kind of lean on what we've drawn for part A. So where do you expect this to be a linear function? And the short answer is, on every single one of these intervals. So we can write those things down here. So for part B, what intervals do we have? Well, what's our first interval if we read from left to right? So that is negative 3.5, which is less than x, which is less than negative 2. I'm going to write one more interval, and then we'll talk about one of the ways I'm representing here. The second interval is going to start at negative 2 and continue on to x equals or 0. Now, I have inequalities here, and if you'll notice, I am not including the endpoints for any of these intervals. Why is that? So the reason for that is, one of the things you'll talk about in this module is how to tell if a function is differentiable. And a function is differentiable only, if that limit definition of a derivative, if that limit exists. So let's look at the derivative graph here. If we look at, I'd illustrate this in a couple of different points, but let's do this. What is the limit as x approaches negative 2 of g prime of x? Well, to talk about that, let's talk about the one-sided limits. What's the limit as x approaches negative 2 of, or from the left of g prime of x, and as we approach it from the right? Well, if we look at this point of negative 2 and approach it from the left, I think we have a derivative of positive 1. But if we approach it from the right, we have a limit of negative 1. So the one-sided limits both exist, but they don't agree with each other. So what does that mean about the limit, the two-sided limit? Well, that means that doesn't exist. And if that limit doesn't exist, then we say our function is not differentiable at that point. And if we have a function that's not differentiable at a point, then that means its derivative doesn't exist there. And one of the ways that looks on a graph is you'll get these hard corners, these hard cusps, instead of like a smooth curve. But in terms of answering part B, all of these, all 4 of these little subintervals are going to be linear. But we can't really talk about that. We can't really extend that linearity to those corners because, the derivative can't be defined there. We can't really talk about the behavior at those endpoints. So 0 to 2, and also from 2 to 3.5. All right, moving on to part C. At what values of x is g prime of x not defined? So this is, we just talked about this, but now we'll talk about it in using slightly different language. Where is g prime of x not defined? Well, that'll be x equals negative 2, 0, and 2. And to answer that question, one of the ways we can think about it is look at the graph of g prime of x. What values or what x values are not in the domain for g prime? And that would be anywhere where the x value does not return a y value. So these open circles indicate that they're like, there is no other point where the derivative is otherwise defined. For example, there's not like some other y value that has a closed circle at it, but the derivative is not defined at x equals negative 2, 0, and 2. So that means our function is not differentiable at those 3 x values. So what does that look like? Well, in our specific case, we have hard corners. We have places where, one thing I keep going back to when we talk about derivative is, especially on a graph, you can think about slope and a tangent line. So can I make a tangent line at these hard corners? The answer you might be tempted to say is, well, sure, yes, I can. In fact, I just did it. But here's the problem. I can't make a unique tangent line. I can make lots of lines that are going to glance at this point and only touch it in one place. So that's one of the things to think about is if the slope of the tangent line exists, it can only be one value. And in these cases, I can't get a unique one. So it's another way to think about having a lack of differentiability on a function at a point. And finally, part D, suppose that g not equals 1. So now I'm learning that I got ahead of myself. So now we are given a point that our graph must go through. So let's see how we did. G of 0 equals 1. So my graph clearly does not meet that. But here's the good news. I know from the derivatives exactly what shape this graph has to have. So I can kind of mimic what I've already drawn. But from here, I know that this is a point that has to belong on my graph. But I've already done kind of all the analysis that comes from the derivative. So I can basically translate the graph I've already drawn upward to arrive at the graph they want. And while I'm doing this, I'll use this to kind of highlight the fact that a derivative gives you a rate of change. And rate of change is a valuable thing to know to talk about the behavior of a function and how to draw its graph. But what the rate of change cannot tell you is where something is. I'll give you kind of a silly example that I've used before. If I tell you that a car is driving 100 miles an hour, there's no way for you to know where that's happening. Is it Arizona? Is it the moon? So rate of change, again, it's a valuable piece of information, but can't tell you a complete picture. So yeah, even though we did this for part A, kind of got ahead of ourselves, this is the graph we really run for part D. So this is one thing we'll talk about later in this class, but when you're trying to construct a function from its derivative, you can only do so much without knowing where that graph is, or like you have to know like some data about the points that are on that function.